A warm new welcome to a warm new video. This time we're going to revisit the binomial expansion from year 12. So we're going to have a look at year 13 version of what should already be very familiar to you. So it's a fairly short chapter, this, only 3 subsections. So what we're going to do first of all is obviously have a few warm-up questions, and then we're going to explore how we can adapt the year 12 version of a binomial expansion to give us a new version which will work for both fractional and negative powers of an exponent. So, like I say, let's get warmed up first. Here's 4 questions for you to try. The first 2, fairly quick, fairly straightforward. 3 and 4, much more expansive. So pause the video now, have a go at these on your own, and when you're ready to see the solutions, press play, and I'll guide you through how you can arrive at the solutions to each. Okay then, so without messing around anymore, let's have a look straight away at question number 1. Here, we need to show that x squared minus 8x plus 18 is greater than 0 for all x element of real numbers. So this is just saying for all real values of x. Now this is very little more than completing the square in a slightly differently worded way. So what I can do first of all is complete the square on these x terms. So we get x squared minus 8x plus 18. Now the x squared, we just put an x in the bracket. We half the coefficient of the x term, so half of negative 8 is negative 4. We square all of that, and then we subtract off this value here squared. Well, minus 4 times minus 4 is positive 16, so we subtract off that 16. So all we've done here is we rewrote this like this, but then of course we have the plus 18 at the end to contend with as well. So this will now simplify, so we have x minus 4 all squared, and minus 16 plus 18 gives us plus 2. We can now conclude and finish off our proof. So the first thing I'd suggest saying is that x minus 4 all squared has to be at least 0. And so if we add 2 to that, then x minus 4 squared plus 2 has to be at least 2, and obviously 2 is greater than 0, which is what we wanted to prove all along. Then just return to the original statement and say, therefore, x squared minus 8x plus 18 must be greater than 0 for all x elements of real numbers, which is exactly what we wanted to do, so we've proved it. That's question 1 done. Question 2, a very quick application and reminder of what the factor theorem is. So what we do here, instead of minus 3, we try f of positive 3. If that gives us an answer of 0, then by the factor theorem, that proves that x minus 3 is a root. So all we need to do here is just sub in when x is 3. So x cubed becomes 3 cubed, x squared becomes 3 squared, and so on. This gives us 3 cubed plus 3 squared minus 8 times 3 minus 12. Because it's proved that, it can't hurt to just show a few more steps in our working just to make it absolutely clear. So 3 cubed is 27, 3 squared is 9, 8 times 3 is 24, and obviously minus 12. Now that will come to 0. This is 36. Take away 24, take away 12 is 36. Take away 36, which is 0. So therefore we can say that x minus 3 is a factor of f of x by the factor theorem. Books and brackets, this strictly speaking isn't needed to say by the factor theorem, but I'm just showing you that's what we've used to prove it. But it's implied in this working up to this step. Let's have a look now at warm-up question 3. So for number 3, we've got a line with equation y equals 3x plus 20. It cuts the curve with equation y equals x squared plus 6x plus 10 of the points A and B as shown below. What we need to do here is to show algebraically that the coordinates of A and B are -5, 5, and 2, 26. So A is this one here, and B is this coordinate here. So we're trying to show that A is -5, 5, and B is 2, 26. So A and B are where this straight line meets the curve. And that will happen when the straight line with this equation is exactly the same as the expression for the curve with this equation. So we set one equal to the other. So we're going to say let 3x plus 20 equal x squared plus 6x plus 10. If we solve this, this will tell us the coordinates, the x-coordinates at least, of A and B. Let's show that question, so let's stay clear of the calculator and try and show this algebraically. We can get this into a standard quadratic form by getting it all onto one side equaling 0. So if I subtract 3x and the 20 from both sides, I'll have 0 equals x squared plus 3x minus 10. Now you should see that on this right hand side this will factorise. You could use your class words at this stage, but it's fairly straightforward even without doing. Two numbers that multiply together to give -10 and add up to +3, those two numbers would be +5 and -2. And so this quadratic factorises into this form. So 0 equals this bracket multiplied by that bracket. Therefore, one bracket has to be equal to 0, either one or the other. So if this bracket's equal to 0, we'd have x equals -5. Or for this one, x would be 2 to make this final bracket equal to 0. So either x equals -5 or x equals 2. So we're halfway there. We've got the x-coordinates of A and B. To find the y-coordinates, we sub in each value into one of the initial equations, either for the straight line or the curve. It doesn't matter which. I'd suggest the equation for the straight line is easier, so I'm going to suggest we substitute our x values into this equation for the straight line. So now, for this one, if I sub x equals -5 into y equals 3x plus 20, I'm going to get y equals 3 times -5 plus 20. 3 times -5 is -15. -15 plus 20 is -5. So therefore plus 5. -15 plus 20, my apologies, gives us +5. So therefore A must be when x is -5 and y is +5. Same idea for B. We just sub in x equals 2 into either equation. I'll pick the same one. I'll pick the equation of a straight line. Y equals 3x plus 20. So the corresponding value for y when x is 2 is y will be 3 times 2 plus 20, which is much easier to see. Because 3 times 2 is 6. Then 6 add 20 gives us 26. So therefore B equals 2 and 26. Now part 4, warm-up question 4, relates to warm-up question 3. So we're going to use the information from question 3 to help us for question 4. So question 4, using the information given in question 3, use calculus to show that the exact area of region S, this region here with the diagonal lines, is 57 1/6 square units. So let's just add the information in what we got from question 3. So we're told A is -5, 5, and we worked out that B was 2, 26. Now in between -5 and 2, we can think of this whole shape being encapsulated in a trapezium, which we're going to highlight in red like this. So this whole area you can think of as being the red trapezium, but I only want this shaded region S. So I don't want this bit underneath the quadratic curve, which I'm going to colour in yellow. So this bit here, I don't want that. So what's left, this region here, which I'm going to put in a nicer green, I can think of as this green region, S, which is what I'm trying to find, as being this whole trapezium with this yellow area subtracted. In other words, S is the whole trapezium minus the area underneath the curve, as follows. So we can apply some calculus carefully to work out what this is and evaluate it, and it should come as 57 1/6. So first of all, the area of trapezium. Well, what we need, the ingredients for the area of trapezium are the distance from the parallel sides, often called the height. This in a way is its width because it's laid on its side. And we need to know the height or lengths of each parallel side. So what we do know is the x-coordinate here is 5, so that side of the trapezium has height 5. This x-coordinate is 26, so this side of the trapezium has height 26. And from x being -5 up to x being 2, this must have a width of 7. So for a trapezium, the area is half of the two parallel sides added together, so it's half of 5 plus 26 multiplied by the perpendicular distance between the two parallel sides, so we multiply it by 7, and then we subtract the area underneath this curve. So the area in between the x-axis and a curve is what we get when we integrate the curve with respect to x. So the curve has equation x squared plus 6x plus 10, so I'm going to integrate that with respect to x in between the limits where here x is -5 and here where x is 2. So that's what we're going to have to compute now. We can't just type it into the calculator, we need to show clearly because it says show that question. So what we can do first of all is work out this easily enough. Half times 5 plus 26 times 7. So we can do this bit, to be fair, fairly straightforwardly. So we've got half of 5 plus 26 times 7. That bit gives us 217/12. And over here, I'm going to integrate between these limits. So we increase the power of x by 1 and divide through by the new power. So x squared becomes x cubed over 3. 6x, I replace the x with x squared and divide through by 2. So 6x squared divided by 2 gives us 3x squared. And this constant 10 just becomes 10x. So I'm integrating that in between the limits of 2 and -5. So just doing it step by step, nice and slowly. 217/2. I'm going to subtract off everything here. So when x is 2, x cubed is 8, so that's 8/3 plus 3 times 2 squared plus 10 times 2, which is 20. I'm going to minus off from that when x is -5. So x cubed is -125/3. And 3 times x squared, well, if x is -5, x squared will be 25. 3 times 25 is 75. And then 10 times -5 is -50. So this will give us 217/2. Then this here, 8/3 plus 3 times 2 squared plus 20. Let's work that out. So 8 over 3 plus 3 times 2 squared plus 20. That gives us 104 over 3. So we can put this in as well. But I'm minusing whatever this is here. So now we type this in. So minus 125 over 3 plus 75 minus 50 gives minus 50 over 3. So minus 50 over 3, I can think of as being plus 50 over 3. Now we can finally just give an answer to this. So what we're going to have here is 217 over 2 then minus, in brackets, 104 over 3 plus 50 over 3 that gives me 343 over 6, which seems slightly disconcerting. That's not the answer we need. However, with a crafty application of the S arrow D button here, if I press Shift S arrow D, it'll convert into a mixed number for me, and thankfully it is 57 1/6, which we wanted to show all along. So I've shown it, so we're done. So we've completed the warm-up. So let's have a look at revisiting this binomial expansion. So we can derive a new expansion from our existing one. So for year 13, we need to know the expansion of 1 plus x to the power n. That's a half lie. You are actually told it, but what you do need to know is now how to apply it. So I'm saying here in year 1, we discovered that if n is a natural number, you can find the expansion for a plus b to the power n using this formula here. So that was based off Pascal's triangle. You should have seen this, in fact you will have seen it in year 12. It's not too hard once you get used to it, but it only works for natural numbers. The idea here is, can we go from a binomial expansion for only natural numbers and expand it so that we can have an expansion where we can use not just only natural numbers, but fractional numbers and negative ones as well. So to do that, for our first step, what we're going to do is we can just replace a with 1 and b with x. So let's do that first of all. So exactly what we have here, a plus b to the power n will become 1 plus x to the power n. So a to the n is just obviously 1 to the n. Then we can have n choose 1 of a to the power n minus 1. b is now x plus n choose 2, 1 to the power n minus 2. I know you're probably thinking this is just one row, isn't it? It is, but I'm going to get onto that in a moment. Then x squared and plus so on and so forth. In fact, I'll do an extra one. I'll do n choose 3. That'll be 1 to the n minus 3 x cubed. I'm going to leave these n terms alone. You'll understand why in a moment. So that's step 1. All I've done here is just subbed in a as being 1 and b as being x. That's all we've done here. So step 2, we can now use the definition for what n choose 1, n choose 2 is in terms of factorials. So again, this was mentioned in year 12. So n choose r is n factorial. So if n were 5, that means 5 times 4 times 3 times 2 times 1. Then that's divided by r factorial multiplied by n minus r factorial. So what we're going to do here, we're going to place all these instances of n choose r, all of these, with their factorial versions. So next step, 1 plus x to the n, that's going to be 1 to the n. N choose 1 will mean n factorial over 1 factorial, brackets n minus 1 factorial. That's times 1 to the power n minus 1 x. And this next one, n choose 2, can say as n factorial divided by 2 factorial brackets n minus 2 factorial. 1 to the n minus 2 x squared. And then for the cube term, n choose 3 is n factorial divided by 3 factorial brackets n minus 3 factorial. That's multiplied by 1 to the n minus 3 x cubed, and of course it keeps going and going and going. So now what we're going to do is simplify. For step 3, we're going to simplify everything above in step 2. So 1 to the power n is always just 1. So we're always going to start with 1. Now this here, I've got n factorial, which I'll just write here to the side. So n factorial, that equals n times n minus 1 times n minus 2, all the way down to times n by 1. That's what n factorial is. So n minus 1 factorial, for example, is the same idea, but we'd start at n minus 1 and go down accordingly. So I have n minus 1, n minus 2, n minus 3, all the way down until we're times n by 1 again. So if we do n factorial divide by n minus 1 factorial, this n minus 1, n minus 2 and everything beyond will cancel. So it'll all just cancel off. So n factorial divided by n minus 1 factorial. The only thing we're going to be left with is just this n at the start. And 1 factorial is just 1. So all this becomes 1. So it becomes n times 1 times x. So that becomes plus nx. So get 1 plus nx, like so. For next term, n factorial over 2 factorial, n minus 2 factorial. Well, n minus 2 factorial would start from here. So n factorial divided by n minus 2 factorial would look something like this. So if I just show you the cancellations, in case you're not sure. And what I'd have on the top, n minus 1, n minus 2, all the way down to 1. On the bottom, we start from n minus 2, so I have n minus 2, n minus 3, n minus 4, and so on, all the way down to times n by 1. So the n minus 2s and lower would all cancel. So we'll just have n minus 1. So all this here will become n brackets n minus 1. But I'm still dividing by that 2 factorial. X squared. And in a similar way, this one here will also cancel down a lot, because anything n minus 3 and below will cancel. So I'll just be left with n minus 1, n minus 2 on the numerator, and the denominator will be left with a 3 factorial x cubed. And this here is an infinite expansion, so I'll explain why right now. So in your box here, this is what you need to know how to apply, which we're going to practice with lots of worked examples in just a moment. So why is this an infinite expansion and the original one for year 12 was not? Well, what we're trying here is using the idea that x isn't a natural number. So for example, what if it were a fraction or something like this? So if n isn't a natural number, these terms here will never cancel off. So for example, if n were a fraction, this would never just cease to be, because this will carry on indefinitely. And because n is not a natural number, if we're using this year 13 version, then n will never be a factor of anything in these brackets. So these brackets multiplied together will never be equal to 0. For example, if n were 1, this would be equal to 0, then we'd stop here. If n were equal to 2, that would be equal to 0, so then we'd stop at up to this point here. But because it's always going to be a fraction, if we're using this year 13 version, then this expansion will be infinite. So this here is the form we use for year 13. So I'll explain in a bit more depth what I mean by using this form here. So this new definition for the binomial expansion of 1 plus x to the n removes the restriction on n having to be a positive integer, and therefore opens up the possibility to explore other expansions, for example when n is negative, fractional, or both. Also note this expansion computes an infinite series for any n being a real number, and as the series progresses, therefore, the power of n in each successive term increases, so that this power of n will approach infinity. So what does this mean? Well, from chapter 3, the one we just did, sequences and series, we saw that a geometric series with common ratio r and first term a, which will always look like this, a plus ar squared plus ar cubed and so on, will only converge when the magnitude of a common ratio is less than 1. So in the same way, this generalized binomial expansion for 1 plus x to the n will only converge to a meaningful value if the magnitude of this second term, the magnitude of x, is less than 1. If the magnitude is less than 1, it will converge to the actual value of what we're expanding. If not, it will diverge off to infinity. So that's the restriction we need to be mindful of when using this binomial expansion. So we can also generalize it further in case x has a non-unitary coefficient. For example, what if we're expanding 1 plus 2x to the power n, or 1 plus 4x to the power n? So it's very simple to adapt. So the general binomial expansion for 1 plus ax to the power n is valid only for when the magnitude of ax is less than 1. Then dividing through by magnitude of a, that's the same as saying that the magnitude of x is less than the magnitude of 1 divided by a. So the range of validity, this is often called. So we are often asked in an exam, often it's a 1-mark question, to give a range of values of x for which the expansion is valid, and sometimes, like I've said, this is referred to as the range of validity of the expansion. So that might seem confusing for now, so let's deconfuse and simplify with some worked examples. So first worked example. Find the first 4 terms in the binomial expansion of 1 over 1 plus x, and state the range of x for which this expansion is valid. Well, for this worked example, I think it's just worth me reminding you again that the formula is given to you, so you don't need to worry too much about remembering it. It's just a case of knowing how to apply it. So here's a formula as taken from the formula book kindly provided by Edexcel. Here it is. So all we need to do here is consider this expression in terms of a single power of 1 plus x. So we've got it reciprocal of 1 plus x. So first thing to note is 1 over 1 plus x is one and the same as 1 plus x to the power minus 1. And so we can use this expansion here. Our n in this case is just simply negative 1. So the first term is obviously going to be 1 plus nx, that's going to be plus minus 1 lots of x. Then the next thing will be minus 1 times minus 2 all over 1 times 2, which is 2 factorial, if you want to leave it in factorial notation, x squared, and then minus 1, 1 less than minus 1 is minus 2, 1 less than minus 2 is minus 3, 1, 2, 3 terms, so divide that by 3 factorial. That's why I prefer the factorial idea. The number of terms on the top is the same as what we're taking back factorial of. So 3 terms, 3 factorial, 2 terms, which is 2 factorial. And that's going to be our coefficient of x cubed. And of course it would keep going, but we're just asked for the first 4 terms, so 1, 2, 3, 4, and we're good. So this just gives us next, we've got 1 minus 1 times x is minus x, minus 1 times minus 2 gives plus 2, 2 divided by 2 factorial gives 1, so I've got positive 1x squared. And this one here, minus 1 times minus 2 times minus 3, that gives minus 6. 3 factorial is 6, so minus 6 divided by 6 is minus 1 x cubed. So those are the first 4 terms as we were asked for. State the range of x for which this expansion is valid. So we just need to put in here that the size of x has to be less than 1. Or you could say it like this. Same difference, either this or that will be absolutely fine. Work example 2. So before I start off with work example 2, I'm just going to mention that sometimes it's useful to modify this definition of a binomial expansion to avoid confusion when making substitutions. So, for example, if it wasn't just an x here, but it was like a 4x like we've got here, or a 10x or something awkward, just replace the 4x's or the whatever number of x's with a single term. Call it, for example, b. Then it works in the same way, just with this b replacing the x in the standard definition you're given to on the formula book. So here what we could say is we could let our b be 4x. Because we've got 4x here to expand. So we're just substituting 4x in place of b in this one. So it works in exactly the same way. We're just calling our x b because actually this thing here is more than just an x, it's 4x. But whatever it is, you treat it in the same way. You treat the 4x as just one whole thing to put into your expansion. So let's do this here, and you'll see it's actually very straightforward. So we've got 1 over 1 plus 4x squared. So I need to have it in terms of 1 plus something all to a power. So if it's 1 over something squared, that's a reciprocal of this thing squared. So it's 1 plus 4x to the power minus 2. Now we just proceed as normal. So up to the x cubed term, the first term is always going to be 1. Then we've got the power multiplied by our b in this case. So it's going to be minus 2 times 4x. And then after that, we're going to have minus 2 times minus 3 all over 2 factorial, and that multiplied by 4x all squared. And finally, the x cubed term will be minus 2, minus 3, minus 4, all over 3 factorial, all of that multiplied by 4x cubed. Also, that's going to go on and on and on. But because these terms will reduce in value, we can get an approximation by just taking these first 4 terms. So we can say that's about the same, approximately 1 minus 2 times 4x, that's going to be minus 8x's. At this stage now, I'll show you what these look like on a calculator. So on a calculator, what we need to do is minus 2 times minus 3 divided by 2 factorial, so 2, then shift the reciprocal button, then times that by 4 squared, that'll tell us the coefficient of x squared. So we get 48x squared. And the last one, minus 2 times minus 3 times minus 4, we can just adapt what we have at the top. Whoops. So times again by another negative 4. All of that now is under 3 factorial, like so. But now it's going to be times by 4 cubed. And if we do that, we'd get negative 256x cubed. So that there is the expansion of 1 over 1 plus 4x squared for the first 4 terms, or in other words, up to the terms in x cubed. Question 3. Now we need to find the x cubed term and state the range of validity for x for the expansion 1 minus x all cubed rooted. So this one here, we can rewrite it. So the cube root of something is the same as this thing here, all to the power of 1/3. So if I just bring this out of the way for a moment, because I can use this with our definition for the new general binomial expansion. So if we just take the cube root of 1 minus x and think of it like this, then we can use this here to help us out. So instead of a positive x, we've now got a minus x, but we treat it in exactly the same way. There's no problem whatsoever. So what we're going to have here is the first term is going to be 1, obviously. Then it's going to be the power multiplied by x, or whatever is after the 1 is what you need to think of it as. So this time the power is 1/3. Now in our case, our positive x is actually a minus x. So it's going to be n times minus x, like so. Then we're going to have the power multiplied by the power minus 1. So 1/3 minus 1 is minus 2/3. We're going to have all of that over 2 factorial multiplied by minus x all squared. And go again. 1/3. 1/3 minus 1 is minus 2/3. Minus 2/3 take another one is minus 5/3. All of that over 3 factorial. And that's going to be multiplied by minus x cubed. And obviously this is going to go on and on and on. But we're just asked for the first 4 terms, essentially everything up to the x cubed term. So if we work this out now, it's pretty simple to do. So 1/3 times minus x is minus x over 3. This next one, I'll show on a calculator, in fact, why not? So we've got 1/3 times minus 2/3. And all of that we're going to divide by 2 factorial. So divide by 2, shift factorial. We get minus 1/9. So it's minus 1/9 of x squared, or minus x squared over 9, if you want to write it like that. And this one, minus x cubed will give us minus x cubed. So that's going to be a negative term. And this here is going to be positive. So again, it's going to be a minus here. So we do 1/3 times minus 2/3 times minus 5/3 all over 3 factorial. So on a calculator, what we could do is this. So we've got 1/3 times by minus 2/3 multiplied by, as you can see there, minus 5/3. And all of that is going to be over 3 shift factorial. We get there 5 over 81, so it's minus 5x cubed over 81. And for this one, the range of validity is simply that minus x has to be, the size of minus x needs to be less than 1. In other words, the magnitude of x itself has to be less than 1. So this is the expansion we get, and the range of validity is this over here. Slightly trickier example now. What if you have a function which is a composite? You've got a numerator which in itself is a function of x, and you're dividing by something which we need to do a binomial expansion of. So how would you do this one? How would we find the x squared term in this series expansion? Well, again, just to remind you of the binomial expansion for year 13. This is what we're working with now in the yellow. So we need to rethink of what f of x actually is. So we need to think of f of x as being 2 plus x multiplied by 1 over the square root of 1 plus 5x. But 1 over the square root, that's a reciprocal of what we're square rooting. So it's going to be 2 plus x times by the square root of 1 plus 5x reciprocal of. So it's going to be not to power half. Power half is when you're square rooting something. Because it's 1 over the square root, it's going to be 1 plus 5x to the power of minus a half. Because it's a reciprocal of a square root. And so what we're going to have here for f of x, we can say that f of x up to the x squared term is going to be 2 plus x. Now we don't do the binomial expansion of 2 plus x, we leave that on its own because that's just to the power 1, which is just itself. We do, however, need to do the binomial expansion on this thing here, which is 1 plus 5x to the power of a half. But bear in mind, we only need to go up to the x squared term, so we don't need to do the whole thing. So the first term of this expansion is also just going to be 1, and the power multiplied by the thing after the 1. So it's going to be minus a half times 5x. Like so. And then it's going to be minus a half times minus 3 over 2, all divided by 2 factorial, multiplied by 5x, all squared. And of course this expansion will carry on to infinity, but because we only want the x squared terms, we can stop after x squared. We don't want to consider x squared terms. So if we just neaten this up now, what's in these square brackets? We've got 2 plus x, but over here we've got 1 minus half times 5, so minus 5 over 2 of an x. And this thing here, let's work out what this is using the calculator. So we've got on the top minus a half multiplied by minus 3 halves, all divided by 2 factorial, and multiply that by 5 squared to find the coefficient of x squared. We get 75 over 8. Now, the x squared term, we'd arrive at an x squared by doing 2 multiplied by the x squared term, and also by taking this x here, multiplied by the x term in this bracket. So therefore, the x squared term is going to be 2 times 75 over 8, so it's going to be 2 lots of 75 over 8x squared plus x multiplied by minus 5 over 2x. So it's going to be something x squared, of course. So now we can just work out the coefficients again using the calculator. So we've got 2 times 75 over 8. So 2 times 75 over 8 is like so. Then we just minus off 5 over 2. And we can see there we get 65 over 4. So it's 65 over 4 x squared, or 65x squared over 4, whichever you prefer. Then finally for b, state the range of values where it's valid. So it's only valid where this 5x, where the modulus of 5x is less than 1. In other words, we want the magnitude of x to be 1 divided by 5 or less. We want the magnitude of x to be less than 1/5, and then the expansion will work and converge to a meaningful value. There's one final thing to mention with these binomial expansions, and that is that they can be used to approximate answers to actual calculations, for example, to approximate roots or awkward powers. So this is an overhang from the old specification. You might be thinking, why do we need to do this? We have calculators these days. Well, it's sort of a lens into the history of maths. This is how we could compute roots before we had calculators, essentially, or at least valid estimations to roots. So let's have a look now, worked example 5 in a sense. So how can we use a binomial expansion to estimate values? Well, here we've got f of x, which is 15 over the root of 1 minus x. Firstly, we need to find the binomial expansion of f of x up to the terms in x cubed. Then b, we sub in x equals 0.1 to find an estimate to root 10, giving answers to 5 decimal places. And finally, part C, we need to use a calculator to work out the percentage error in the estimate we've just worked out. And again, this time we're going to give that answer to 3 significant figures. So just to remind what we had from before, this new general binomial expansion is this thing here. Now what I'm going to suggest to do, I'm going to section this out into 3 bits. So we've got plenty of space for an answer for each section. And if I don't, then well, I've made another mistake. But let's see how we do. So first of all, find the general binomial expansion of this up to the terms in x cubed. So for a, what I need to do is think of f of x in a different way. So this is f of x. I need to think of that as being 15 multiplied by 1 over the square root of 1 minus x. That's the same as saying it's 15 multiplied by the reciprocal of the square root. The square root is a half, so 1 over a square root means it's power of minus a half. So that's what we try and do the expansion of here. So f of x is 15 lots of the binomial expansion of the square root of 1 minus x to the power minus a half. So we want to go up to x cubed. So it's 1 plus the power, which is minus a half. So it's that multiplied by, now it's minus x we've got here, you see. So it's minus a half times minus x. And the next one, minus a half times minus 3 over 2, all over 2 factorial. Then it's going to be minus x squared. I'm going to move this along because I've got enough space in the end. If I don't, like I say, I've made another mistake, but I'm going to think I'm going to do this actually, without just running out of space and making my writing absolutely tiny. The final one, up to x cubed, we're going to have minus a half. 1 less than minus half is minus 3 over 2. 1 less than minus 3 over 2 is minus 5 over 2. All of that now divided by 3 factorial, then minus x cubed. So again, this can obviously be much neatened up. So we've got 15, then in these squared brackets we've got 1. Minus half times minus x is plus x over 2. This next one, again we're going to have a positive power, so the half times 3 over 2 over 2 factorial. It says minus a half, doesn't it? It says minus a half times minus 3 over 2. All over 2 shift factorial, and then we had again, just times minus x squared. So that becomes 3/8. So that's 3x squared over 8. And the last one, we're times it by another minus 5/2 at the end. Now divided by 3 factorial, so I'll edit that to a 3. And again, this will pop out as a positive value because minus x times minus x times minus x gives minus x cubed. That times another minus gives us a plus. That's going to be positive 5/16 x cubed, or just plus 5x cubed over 16. If we then expand this all by 15, 15 times 1 gives 15. 15x over 2 is, well, like I've said, 15x over 2. 15 times 3x squared over 8 gives 45x squared over 8. And lastly, 15 times 5 is 75, so we get 75x cubed all over 16. Now, part B, it says sub in x equals 0.1 into this expansion to estimate the value of root 10. So, for B, we think when x is 0.1, what we're going to have. In fact, I'm going to admit defeat, I'm going to get rid of that. I've not quite managed it. Never mind. When x is 0.1, what would fx actually be? Well, fx is going to be 15 divided by the square root of 1 minus 0.1. Now, 1 minus 0.1 is 0.9. 0.9 I'm going to think of as being 9/10. So the square root of 1 minus 0.1 is the same as the square root of 9 over 10. I can square root 9, that's 3. The square root of 10, I just leave as the square root of 10. So 15 divided by 3 over root 10 would give us this. And if you're not sure, try on a calculator. We've got 15. I divide that by the fraction 3 over the square root of 10. This root 10 will pop to the front, so it's going to be 15 divided by 3. It's going to be 5 lots of root 10. So f of x, when x is 0.1, would give us an answer to 5 root 10. And also as well, from the expansion, if we put this into expansion when x is 0.1, we get f of 0.1, approximately, because obviously this is an infinite expansion, we get 15 plus 15 lots of 0.1 over 2 plus 45 lots of 0.1 squared over 8, and then 75 lots of 0.1 cubed all over 16. And so let's see what this gives us. So 15 plus 15 times 0.1 all over 2, then plus 45 times 0.1 squared all over 8, and then finally 75 times 0.1 cubed all over 16. We get 10,119 over 640. So we've got that when x is 0.1, f of x should give us 5 root 10. And when we use the expansion for when x is 0.1, we get f of x is this. So therefore, we equate these two. So therefore, 5 root 10, using our expansion as the estimator, should be 10,119 all over 640. So therefore, root 10 equals 10,119 over 640 divided by 5. So this answer we just got, divide that by 5. We have this, press S arrow D, we need it to 5 decimal places, we get 3.16219. 3.16219. Then finally, for part C, it says use your calculator to work out the percentage error of your estimate. Give your answer to 3 significant figures. Well, root 10 on the calculator, let's see what that actually gives us. So square root of 10 equals 3.1622. What else does it say? 7766. We now need to remember percentage change calculation from GCSE, whether it be a change, an error, percentage profit, whatever. The percentage of whatever equals the whatever, in this case the error, divided by the original or actual. So in our case it's the actual value multiplied by 100. So the actual error is going to be the difference in between what root 10 actually is on the calculator. So that's 3.16227766 minus this expansion estimate, which we had was 3.16219. All of that divided by the actual answer, which is, of course, 3.162227766. That's the fractional error. Get the percentage error and multiply that by 100. So let's try this and see what we arrive at. So that's the actual. So percentage error is that answer I've just got stored, minus the 3.16219 I got from before, divided by my answer for root 10, which I have stored, which I can type in as root 10 if I want to, and that multiplied by 100, not 1,000, will give 2.77 times 10 to the minus 3, and that's a percentage. So as an actual percentage, 10 to the minus 3 means 0.00, so it's going to be 0.00277%. So even by just taking the first 3 terms, we get a very, very accurate approximation to an otherwise awkward expansion, which would be very hard, incredibly hard, if you imagine not having a calculator when doing so. So that's all we need for 4.1. It's now over for you to try some questions on your own. So in your books, if you turn to page 96, exercise 4a, start from question 1a, c, e, then question 2, then 4, 5, 6, and finally 8 and 9. If you get stuck, check the back and check your answers. If you're still stuck, ask one of your classmates, and of course, if you're still stuck, ask me either on an email or in person in lessons, or even in a comment on this video. So thank you very much for watching. Do please like and subscribe, and I'll see you in class very soon. So take care and bye for now.